Presentation from Vlatko from Hotline Labs.
Hello. Oh. So good afternoon, everybody. My name is Vlatko and I'm the founder and CTO of a small startup company on the other end of the world in New Zealand called Hotline Labs. So I believe I can claim the title of the person who has traveled the most to be here, effectively 20,000 kilometers. And it's really good to be here because New Zealand is very small and here feels like everything is going on. This biotransition is real, whereas back at home it's a little bit more of a struggle. Anyway, so today I will actually give you two presentations for the price of one. The first one will be about the topic of the global greenhouse potential for CCU and S. So people talk about using CO2 in greenhouses, but the question I'll try to answer is how big can this possibly be and why is it important? And the second part of my presentation will be about telling you what Hotline Labs, my company, is doing to try and achieve this potential. So first of all, just a bit of context. When we're talking about greenhouses, we're not talking about your uncle's backyard plastic greenhouse. This is high-tech, hydroponic, multi-hectare operations, like the ones you probably would have seen in Holland. If you look on this picture, there's these little dots that you can see crossing. These are actually street lights. So what you're looking at is about 350 hectares of LED-lit greenhouses. So one of these greenhouses will have like 5 megawatts of power installed to generate lights for their plants. So this is quite next level. This is actually a huge industry worldwide, just the high-tech sector. There's at least 60 to 90,000 hectares of greenhouses growing all over the world. And this is not talking about the medium scale and the smaller technology like your uncle's backyard greenhouse. They're producing around $90 billion worth of crops, and it's largely tomatoes, capsicum, cucumbers, as well as flowers, and now increasingly cannabis, which is obviously a very revenue-generating crop. One actually surprising feature of greenhouses is that they are very resilient to climate change by definition. They're able to grow in all sorts of conditions, and they're also able to grow very close to cities. So in many ways, they reduce the transport costs because you're able to grow tomatoes in Holland instead of growing in Morocco and then shipping it 2,000 kilometers. So the reason for their incredible success is the crazy productivity these can achieve. So a modern greenhouse, like the one you can see here, routinely grows over 50 kilos of tomatoes per square meter. So if you look at this picture, you can consider that they can fill up this whole place up to this gentleman's waist in tomatoes every year. And the reason they can do that is because, much like humans, plants grow a lot better when they live inside a house, then the temperature is controlled, when they have all the fertilizers and supplements they need to grow, up to a point where actually the amount of CO2 in the greenhouse becomes the bottleneck for plant growth. So growers have worked that out since the 80s and have been adding CO2 inside the greenhouse to feed the plants and make them grow up to 20 to 40% faster, as Sonia said earlier. The kind of concentrations they reach in there are really safe. They never go above 1,000 ppm because the plants don't like it, and humans, that's the level where humans start yawning. You have been exposed in many a meeting room to this level of CO2 and quite safely. So why is this important for CCU? I personally was working on carbon capture for decades in research for power plants, and the struggle is that it's too expensive for anybody to want to pay money to not emit CO2. But one day I walked into a greenhouse and realized that there are people here who are very happy to pay 150 euros a ton of CO2 because it will generate them 200 euros worth of tomatoes more. And so I was like, oh, okay, this is what we've been looking for. And on top of that, they don't need the CO2 to be pure, really. They only need it to be clean enough. Obviously, you can't put a car or a biomass boiler inside it directly because the smaller pollutants will hurt the plants. So what they needed is a source of clean CO2, not pure, which makes the job even easier. However, one intriguing fact, and I'm going to skip this slide, please don't spend too much time on it, it's really difficult, is the demand of the CO2 and heat demand of a greenhouse are decoupled. So typically plants grow during the day, not during the night, but they need most of their heating during the night. And conversely, in winter, they need much more heating, but there's not so much sun, so they use less CO2. So it's quite a very complicated subject, and things get even harder when you start using lights or cooling and so forth. But you can summarize this point by looking at an average cold climate greenhouse, 3 hectare greenhouse growing tomatoes. So you can see here on the inlets over the, or the inputs, on the left-hand side, we need to input 36,000 gigajoules per year, which corresponds to about 10,000 megawatt hours, if that's what you prefer to think in. You need to put 360 tons of CO2. It's like a minimum level of enrichment. It can go up to 3 times that. This is the clean CO2 to enhance production. And then you need to put some electricity, not a huge amount, and then fertilizer, labor, etc. But for this analysis, I'm focusing on the heat and CO2. And what comes out and pays for everything else is the 1,500 tons of tomatoes that you generate. So a 3 hectare greenhouse is not very big. The ones that you saw at the beginning were all about 6, 9, 12 in blocks. So the tomatoes pay for everything else, and on top of that, you end up with this green waste. So plants that generate that much crop obviously generate a lot of waste, as well as some plastic waste. And interestingly enough, the emissions of CO2 from the heating, the weight of the CO2 is actually much more than the tomatoes that you have generated. So you can see that the industry has a fossil fuel problem, but it also generates the possibility of replacing the CO2 and doing carbon capture, sequestration, and utilization. So obviously the utilization is simple. If we can supply some CO2 to the greenhouse, they will very happily pay for it. But another aspect we discovered as we were working through this is that this green waste represents a massive potential if it can be turned into biochar. Because if you can do that, then you can start forming an economically positive carbon cascade. So you can see on this slide, on the top left, the CO2 comes out of the sky, is absorbed by the plants. We turn it into char, heat, and CO2 that we get paid for. We get paid for the CO2, paid for the heat. Then the char can be used in a variety of applications, as I'm sure you know about biochar, and finally buried into the ground. Now, the cost of biochar is effectively subsidized by free feedstocks, because we have those 900 tons of green waste to process, and also by the fact that the growers will pay us for the CO2, and also by the fact that we can provide them some of the heat. So it becomes a price negative, carbon negative scheme. And this is very exciting, and this is what my company is working on making a reality. But if you add it up for the whole global industry, you end up with this potential of capturing and storing about 110 million tons a year by 2050. Now, that is actually quite a small amount compared to the target of 20 billion. However, what is really unusual about this is that you can do that while generating value for the growers and for the economy. And this is like no other industry worldwide. So my argument here, which is the message to take home, is that doing CCU in greenhouses is really the low-hanging fruit, because we don't require politicians to agree on subsidies, because the system just funds itself. And this is why we're doing it, and I'm sure that other people will come along for the journey as we go along. So that was part 1 of my presentation. Part 2 is about Hotline Labs, the company that we're working on, and how we are planning to try to achieve some of this potential. So first of all, we've actually developed that central box of the process, which you can feed with crop waste or wood waste. We use a gasifier of our own making that turns that into a syngas and a char, quality char that we can use. And then the whole magic resides in these hot lime materials. So it's essentially a mixture of limestone and iron sand that is a CO2 sponge. I'll tell you a little bit more in a second. But basically what it can do is it can separate CO2 from a mixture of gases. And so that clean CO2 is sent to the greenhouse. The heat we can either use for drying the feedstock or actually supplying to the greenhouse. And the greenhouse sends us the crop waste. So it's kind of like a circular economy setup. This is, we use a fixed bed reactor to make things really, really simple. And that's simply because the demand is not continuous. As I said earlier, plants don't really grow during the night. So during the night, we need to give them heat. During the day, we need to give them CO2. So this is how our machine works. Every night, we turn up the fire. Just waiting for that. Here we go. Turn up the fire and run the gases through this hot lime material, which is effectively a CO2 sponge. So the hot lime material will grab the CO2 and let the other gases go out to the stack. And then during the day, when we want our CO2 back, it's enough to blow some air into it. There's a bit of magic chemistry that happens, and the CO2 now comes out, and it has never seen a fire. So none of the pollutants that were possibly in the fire are now in the CO2, and we can safely feed it to the plants. For those of you who are more technical, we actually use a combination of calcium and chemical looping technology. And if you want to know more about that, come and see me after the presentation. I'd love to talk about it. Our system works with any hot or combustible gas. However, we do need it to be above 700 degrees, which limits the potentials for retrofitting existing boilers. And this is why we prefer to have a package that does everything ourselves. So this is a brief presentation of the system. We have a hopper that takes the feedstock. So we've designed our gasifier to take a variety of feedstocks, primarily the green waste from the greenhouse, but also forestry waste, wet, large, small, etc. It is an updraft gasifier for those who are more technical. And so the feed goes to the gasifier, turns it into a syngas and a char. The biochar we sell. In our case, we actually sell it to animal feed. We've discovered that it helps animals avoid parasites. And New Zealand, as you might know, has vast numbers of cows and sheep. And so we've been actually feeding it to the animals. The gas then goes to a reactor where the hot lime material lives, and it does the CO2 capture separation magic. And then the hot gas goes to a heat exchanger. In this case, we use air. You can do water. And finally, it is directed either to the either to the stack, to the atmosphere if it's during the night, or the CO2 during the day. So I've been working on this for the last 7 years now, and we started off, as many of these technologies do, in a tiny little reactor, making 100 milligrams a day, and we have been scaling up ever since in our labs and workshops. And being in New Zealand, we've actually had to build everything ourselves because it is a tiny place. And over the 7 years, we've taken it from a research scale to a demonstration commercial unit, which makes 3 tons of CO2 a day. That unit is now happily sitting at our first customer, who is stoked, I think is a technical term, finally having access to CO2. Much like your grower, Sonia, the closest other source of CO2 is 400 kilometers away. So he's very happy about that. And you can see our machines there are built out of containers. That is actually on purpose because one of these can cover about 3 hectares of greenhouse, and which is kind of a standard size. And we are looking to do economies by numbers rather than scale, because it makes little sense to make them much bigger. We are planning to make many times the same one and equip a greenhouse with multiple ones. Like this one will actually take the next 2 units for us. So to complete where we are at for Hot Lime Labs, we are finishing off the demonstration unit and optimizing it. And we are preparing, as I said, for doing serial production. So the first units will go to New Zealand, but very quickly we want to come to Europe, because this is where the world's greenhouses are. About 50% of them are here. And we're looking to deploy one next year. And so a bit of a shameless plug. We are looking for investors in the EU to help us get over here, or talking to people to do green finance. We've secured a deal with the New Zealand Green Bank, and I'm sure there are many in Europe doing similar things. And of course, manufacturing partners to help us develop the technology here and install the machines. So that's about all for me today. If you know any one of these people, come and talk to me afterwards. If you have any questions, please ask them. Thank you so much.
Thank you, Vlatko. Do we have any questions on this? No. Yeah, I remember when we discussed that you were planning to move to Europe. What we didn't discuss actually is, and I don't know if you have it in mind, at EU level, actually we have several policies coming up about CCU, and several of them include transport section for CCU. Okay. So I think this goes directly into your business, because you have to transport, you said, up to 400 kilometers.
This actually avoids the transport of CO2. Sorry, I didn't elaborate on this topic, but the only other source for CO2 for greenhouses is purchasing liquid CO2, which typically comes from refineries. Mm-hmm. And if your greenhouse is not close to a refinery, then you end up having to transport it over 400 kilometers. So what we can do is, because we can transform local wood into CO2, we can completely avoid that transport. It's one of the main sort of advantages of our technology.
That's the advantage in most of CCU products, that you kind of use the industry that is next to it.
Yes, that's right.
Hi there. I was just wondering, your project that you've just first set up, have you actually got carbon credits from it yet?
Well, no, this is, as I believe Sarah, sorry, I pronounced her name wrong earlier. It's not actually properly recognized as a CO2 avoided, even though technically it is, because we're displacing something that's of fossil origin by something that isn't. So we're not able to claim any carbon credits for the CO2 avoidance. However, for the char, we are working through the Puro application to get those going. And I think we actually did a life cycle analysis, and our char was proven to be really good, which I was happy about. And it's underway. It's happening now.
Any other question? Remarks from the panelists?
Yeah, thanks. Thanks for the great presentation. And I'm really wondering, you use this gasifier. I haven't seen the incinerator, but I guess you incinerate it in your lime compartment, or is that a mistaken?
It is similar to an incinerator in many ways, but it is actually a typical updraft gasifier. So essentially we put all the fuel in a pile and set fire to it from the bottom. And the gases that it makes are disgusting and usually would not really work. But the reason is that it works for us is we have 10 tons of limestone and iron behind it, and they are capable of oxidizing everything that's left, evening out any oscillations, removing sulfur, removing chlorine. And so basically the bed does the job of evening out and cleaning up the gas. And that makes us able to use like the lowest possible grade gasification technology. And it is very similar to an incinerator, but in our case, our bed of limestone acts as all the cleaning compartment in one step.
Thanks.
Thank you. Well, thank you very much, Vlatko.
Thank you so much. Thank you for your attention.
And now we will hear from Marcel Huber and Ivan DERKINK, who are presenting a joint project from their two companies, so respectively SYNCRAFT Engineering and Bright Renewables.
Yeah, okay. So we have two. Yeah, thanks for taking the time and listening also to our love story, as we called it. And it's quite, I get it very positive that almost at the same time all around the world, it seems that cool things are happening at the same time, which will all foster the same idea, fighting climate change. And this is really great to hear from New Zealand to Spain. It's awesome. We have more or less the same idea. The idea is to evolve bioenergy in a modern form towards something that generates the valuable product platforms defined by green carbon and green soda, we call it, or green CO2. So the bioenergy, in fact, in these plants will be the byproduct in future. You can compare it like a paper mill that turns only a minor share into cellulosic or paper material, and the majority goes to energy, but no one knows that. And I think this is something that happens today, and we have these two pictures representing those things none other renewable energy pathway can generate. So you can't get green carbon or green CO2 from a raw material base other than biomass. And that's quite crucial. So what we can do and what makes bioenergy unique is that this could be done by the way, or otherwise told, the materials are first, and then we have this energy in a side product. And the bubbles are representing, of course, the CO2. We have seen also in Sonia's presentation, the left top picture was beer, so it's quite important. I think even in the beer, the bubble is already renewable, but in mineral waters or Coca-Cola or whatever, it's not. And the other thing is the more stable form. We call it the most stable and the most permanent form of atmospheric CO2 thinkable of. We have heard about a lot in the permanence discussion this before noon. Because what we generate as a biochar is almost like a diamond. So diamond is carbon, and there's one step between what we produce, which is inertinite, or in other ways called graphene, and that's what we are producing. So in both ends, you end up with a very utilizable form in the form of a bubble or in the carbon form. And Bright and SYNCRAFT, we have now a project together to combine both things, because you can do it both in parallel at a single plant, and not only in big scale, but also in a decentralized scale. But I think both of my pre-speeching has said the same. The transportation for local utilization is key. If we have to transport it only by pipelines, and we are build our economy of this renewable soda on pipelines, it might get a big challenge to do it the next 10 or 20 years. And this is the idea what we're going to present today. I just want to, in terms of time management and a very long introduction, I'm sorry, I just want to jump into what we are technically doing. We are producing plants that produce power, heat, biochar, and carbon credits based on the biochar. And what we are built on is we do the opposite that we have heard before. We have developed maybe a more complex gasification system that turns into a multi-stage process, an inhomogeneous fuel like forest residues containing bark, containing needles, into a very homogeneous gas and a very homogeneous biochar. And how do we do that? It's quite simple. We just follow the process that happens with biomass anyway. We pyrolyze it, the first step, with putting some air in. So we turn the biomass into biochar and into a nasty gas. And the thing is that in the second step, we burn these nasty gases. So all the tar issues, all these nasty things, they turn into CO2 and water vapor, nothing more. And combined with the biochar, the carbon we produce, we then recombine these three elements, carbon, CO2, and water vapor, into our synthesis gas and to a pure carbon. And so what happens is that we end up with a third very valuable product stream, which gives you a carbon of about 90, a biochar of about 90% carbon, which all of them is fixed, so very mature inertinite. Then we go to a condensation unit. We end up with a very cold and clean dust-free gas, and that one we can send to the most advanced engines existing at the moment. And we end up with an exhaust gas that we call CCS ready. So it's cool. It has just about 35, 40 degrees. It's moisture, and it's perfectly prepared for a further CCS step. Just showing you some examples of real plants already built. So this has been plant something around number 30. You see another one that's a megawatt plant we built in Austria. It's 8,000 hours already in operation. Then this is our biggest plant we built in Switzerland with 4 megawatt, producing roughly 3,000 to 4,000 tons of biochar a year. You see one in Japan and one in Croatia, just to give you some ideas. We also have in the slides, they will provide it later on as well, some Sankey diagram, just to show you how far we go towards electricity. So the focus is really on producing decentralized electricity at a high efficiency, but also the share of biochar is not neglectable. So it's always important to talk about economics. So we can't compete with a PV installed in big scale in certain places, but that is not the goal. We can also operate and provide this energy on a renewable basis, of course, during night and during winter. And I think when you think about a renewable energy transition, you also have to take care about nights and winter. And this is not a one-stop shop idea, it's an idea of a combined approach where these units can be one piece of a big puzzle to cope with climate change and defossilization. Coming back to this love story, we have up and running almost 40,000 hours operating plant that we will retrofit in Austria. Existing biochar plant. You see the engine, some pictures. These are the rough numbers of this plant. And this we will gonna retrofit with a decentralized CCS unit. What is the reason and why we are so eager to do so? Because we claim to be climate positive, that we are already on a sustainable fuel and on the biochar. But the thing is, we still release 70% of the originally stored CO2 to the atmosphere. Even if it's CO2 neutral, this has to be considered. And when we combine it with a CCS plant, we also produce this green soda, but we only release 14% back to the atmosphere. So that even the level we have, the leverage we have with such a plant is far bigger to go even more climate positive. What to do with biochar? Maybe just a brief info from at that floor. There's a bigger or a better floor at the far right, at the biochar section. But we have companies here that do awesome climate concrete. Castorcon, for example, or Ecoloct. So you really can increase the abilities of concrete. Not only can make it greener, but you can also make it more durable. The inertinite I've said, so it's the most durable thing you can produce to store away CO2. And the prices of biochar compared to all other forms of CO2 sequestration are today a bargain. And this is a matter of fact. So even if you pay 200 euros per ton for the CO2 with a biochar, there is no other path at the moment up and running on a commercial level that compete these prices. When we talk about the durable path, I do not talk about afforestation, which is crucial and important, but we can't credit it, or we shouldn't be very cautious about crediting those things. That's my personal opinion. Yeah, just some numbers, and now I'm sure I'm already over my time, but I'm glad to hand over to letting Ivan explain the back part of our project.
Yes. Thank you, Marcel. So I'm from Bright Renewables. We take care of the other part of the love story, which is the carbon capture part, which works really well with the gasification system of SYNCRAFT. So the love story started for us together with SYNCRAFT with a project in Austria, where we will be producing food-grade CO2, which will be used in a local soda manufacturing. To actually replace fossil fuel CO2. So in terms of the systems we provide, we have two technologies which we can provide, which is the more conventional amine solution, which we use for the bigger systems. So that's up to a 20 megawatts boiler, 20 megawatts biomass boiler. But we also produce smaller systems. So the amine system we produce down to 3 megawatt boiler approximately. But we can also go smaller, but then we switch to a different technology, which is a PSA system. Which main advantage is you don't need any heat, making it more profitable and more economical in a smaller scale. The SYNCRAFT system is exactly in the middle, so we can choose which system we use, depending on the situation. So a brief comparison, very high level between the two technologies. So the capture efficiency is about the same. You can capture a little bit more with the amine scrubber. But the main difference is in the energy usage. So the PSA system uses 0.15 kilowatt hours electrical. And the amine scrubber uses only a third. So it's way less in electrical consumption. But as a trade-off, it does require heat to run, where the PSA requires none, making it very easily integrated, so also easily retrofitted. Then a final comparison is with the CO2 you can produce with a PSA system, because there's not a really physical separation between the raw gas and the product CO2. You cannot get up to food grade quality, so you will produce industrial grade. With the amine scrubber, you can produce food grade. So this is an example of one of the systems we built in the past. And we can also combine them with liquefaction systems. So the carbon capture system is only one part of the solution. In order to be able to use it elsewhere or to transport it, you also have to liquefy it. If you don't liquefy it, you have to use it locally. And for that, we have a separate module which can or cannot be installed on site. So then, very briefly about this economics of the system. So the system we're looking at together is subsidized, and that is also what makes it profitable here. With the subsidy, we have an operational cost of around 80 to 100 euros per ton of CO2, which makes it profitable because the selling price is above that. But without the funding, it doesn't make sense for this scale. For bigger scales, so for the larger scale systems we sell, it does make sense, because then we can get an operational cost of 80 to 100 euros without a subsidy. So the CO2 applications was already mentioned by my previous presenters, but mainly maybe about the biogenic CO2. We are able to capture it with low-grade heat, relatively low-grade heat of below 100 degrees, making it possible to use waste heat, which is available in the SYNCRAFT system and in many other boiler systems. It is a really regional to regional approach, local to local, because then the production matches with the use of the local CO2 users. Together with the SYNCRAFT, you have a CO2 negative approach, because you store CO2 in the biochar, and then the CO2 you emit, you give a further life by using it or by storing it underground, if possible. So I think that sums it up.
Yeah, thank you for your time. Yeah. We are very happy to get questions, and not to forget that we have both booths here. So at B65 you find Bright and Host, and I don't know the number honestly, but you can see the reverse power plant just next to the biochar event zone. But happy to answer any questions right away. Yeah.
Are there questions? No questions. There is a question here.
Hello. I just wanted to ask about the project that you have together. What's the use of CO2 in the end that you're using? Is it for food? Is it for another application? Thank you.
It's used for beverages, for soda.
Okay. Thanks.
Hi. I had a quick question about the amine scrubbers. Are they toxic?
So the chemical itself is harmful for the environment, but it will stay inside the system. So it will be looped inside the system, and it won't end up either in the CO2 or the flue gases. So we contain that by having a washer before on the flue gas side and also on the CO2 side. So we will contain it.
Yeah, for sure. Does that add a lot of cost?
It is included in the cost of the system. So we have one standard module, which includes both the washing before and after.
Cool, thank you.
Maybe to add, ammonia is also used in industrial refrigeration systems quite widely. So it is maybe toxic or harmful, but it is quite a technical fluid which you can deal with.
Hi. Regarding valorizations, why you chose food grade, or I mean beverages, is because you find that they are is market which is more interesting.
Could you speak up, because
sorry.
we
Regarding
can't understand you.
the valorizations, why you chose food grade? I mean the food market is because they are able to pay a premium, or it's because this interested market, or there's a reason?
There's a very honest answer. There are little decentralized applications yet that pay reasonable prices. So that it's far too little. If you produce 3,000 tons, the chemical industry is not dealing with you. And this fits local breweries more or less, or beverage industry. So that's why we go for food grade. But there is a big need for, like we have seen before, for these that evolved, clean but not that high level applications we are looking for, to get a local CCU approach. And if it's a CCUS approach, it's even better. But the problem is the pipeline. We can't wait for the pipeline.
I think it's also a question of location. So this project specifically is located very close to food and beverage industry. But if a different project is located more closely to a greenhouse, then we won't go for food grade, but then for a greenhouse grade.
Really interesting presentation, and I can see how the love story will go a long way. My question was about the smaller pollutants that you may find from the biomass. What happens to the sulfur and the chlorine and the other kind of smaller elements, which I know from greenhouse experience is something that they're really concerned about. So, and second question, sorry, if I can add another one. I didn't quite understand where you were at with your joint, with moving in together with your joint project. Is it already built? Are you looking to build it, or what is the status of your kind of joint operation? Thank you.
The impurities question is quite an important one. The thing is, we deal with wood, with forest residues. So we are not using green waste or whatever. So we only use fuel that is not rich in potassium or chlorine. I think this is also crucial, thinking about biochar and so on, because you find these things then distributed in all and every side streams and mainstreams. So this is, we stay with wood. This is crucial. Then you end up with only some nitrogen shares, but we have a wet scrubber. So we are able to condense even the producer gas without any fears of liquids. And there we get all the ammonia out. So our side stream is ammonium sulfate, by the way, of both things. So we produce as a non-really brought forward thing at the moment, a fertilizer stream. But so we really get down the nitrogen as well in the gas. We have some sulfur, and that is the key also for the CCS part, that we of course have to take care about the SOx and the NOx, and at a certain grade. But that always depends on what you're going to do with the gas. Could be an issue in the greenhouse. And the second question was which stage the project has. We are just about to do this permission work with the government. Project is funded, so we are quite looking forward to do it this year.
Thank you. Is there another question? No. And maybe the speakers would like to have some concluding words? Those who might have encountered me as well, as I always say, it's a really important thing that we approach the whole task together, to fight climate change and to be agnostic technical wise, not to judge too early what is good and what is bad. I think this is the most crucial thing. There is
the opponent or the enemy is the fossil and the CO2 and the ppm in the atmosphere, nothing else. And we have to address it together. And so we really are standing here for demonstrating some kind of love story. But I think this is just something that should happen more often, that even that BEX is not fighting against biochar or direct air capture. There is only one goal. This is just, if you want my call.
Vlatko, Sonia, do you want to say some word?
I cannot agree more with what you say, because it's really important that all these kind of problems we need to face together. And so your joint venture is a clear example of that. And I think that is the path that we need to follow, to be together.
Yeah, I would add much the same. The problem is so large that we should basically just do everything. Every person that has a good idea should just follow it, and it will eventually add up to something. So the little area we deal in is 0.3%, but it takes a whole lifetime just to do that anyway. So we all need to get onto it and work hard.
Thank you. On my side, I think what's really interesting and what your presentation show and the whole day is that there are many different pathways. We talked about CCS, we talked about BEX, we talked about CCU earlier, about fuels mineralization. These are conversion pathways. Now we talked about direct utilization of CO2 in greenhouses. We need to pull all together to make this possible. There are challenges. We've talked about Finland, which is at the, well, above all of us and advancing, showing the way for EU legislations. So, and there are interesting legislation coming up. On the transport part, I think maybe this is one key takeaway here. I think those projects show that for CCU, and it's the case in many CCU projects, generally you can do it close, like the emission part and the final product part can happen close to each other, which is very interesting. There was a question earlier in the session about CCS. Maybe that's the only one of the big differences with CCS, which is do you need to ship the CO2 away in pipelines that we don't always have yet. But thank you all for listening. Please talk to the speakers afterwards. Please